Welcome to the Aeroguy's Aerodynamics series. Get ready to explore the fascinating world of flight as we break down the principles that keep aircraft soaring. Whether you're an aspiring aeronautical engineer, a pilot in training, or an aviation enthusiast, this session will bring you one step closer to mastering the science of aerodynamics. So buckle up, stay curious, and let's take off into today's lesson. Today, we will focus on understanding the standard atmosphere. Understanding the standard atmosphere is essential in aviation, meteorology, and aerospace engineering, as it provides a model of how temperature, pressure, and density change with altitude, allowing for accurate calculations in aircraft performance, flight planning, and aerodynamics. And throughout the discussion, we will also talk about and define altitude, as this is crucial in the understanding of the standard atmosphere. We'll talk about the different types of altitude, such as pressure altitude, density altitude, temperature altitude, as these affect flight operations, engine performance, and weather analysis. And by studying the International Standard Atmosphere, the ISA, we establish a universal reference that ensures consistency in aircraft design, performance testing, and regulatory compliance across the aviation industry. So, let's dive in. The atmosphere, we define it as the firmament. It protects life by blocking harmful radiation from the sun. It helps regulate the Earth's climate. And the lower layer of the atmosphere, particularly at 0 to 11 kilometers and 11 kilometers to 25 kilometers, is where we normally fly our aircraft. Okay. The atmosphere is made up of gases, mainly nitrogen, which takes up 78% of its composition, oxygen 21%, carbon dioxide, water vapor, and other trace gases at 1%. The atmosphere, since it is a gas, it is dynamic. It's constantly moving, constantly changing its conditions. Therefore, the atmosphere is always in a state of flux. The atmosphere, to describe it, we use thermodynamic properties such as density, pressure, and temperature, and we relate all three properties using the equation of state. And due to the nature of the atmosphere, these properties are not constant, but are also changing, as these gases are highly affected by the altitude, the longitude, the latitude, time of day, season, and solar activity. Now, this makes it even more important to establish a standard, a model of the atmosphere, a simplified version or understanding, or a static representation of the Earth's atmosphere, assuming no weather variations, humidity, or wind, making it ideal for engineering and performance calculations. But how did we really get to understand the atmosphere in the first place? Starting with the ancient times, Aristotle tried to describe weather patterns in a study of meteorology. And in the 17th century, we had the invention of the barometer. This proved that air itself has weight and pressure. And over time, in the 18th and 19th century, we developed the first hot air balloon. This allowed us direct atmospheric exploration. And with that invention, we used it to fly our instruments, such as our thermometers or barometers, to get to understand the composition of the air at higher altitudes. And again, over time, the late 19th to the early 20th century, further scientific studies were conducted on the understanding of the atmosphere. And then came World War I and II, which needed states to study aircraft performance to develop a standard understanding of the atmosphere. And finally, in 1952, the International Civil Aviation Organization adopted the International Standard Atmosphere, defining standard values for temperature, pressure, and density at different altitudes. Along with all the data gathering, we established that temperature, pressure, and density changes as we go up to higher altitudes. Looking at temperature, temperature linearly decreases, stabilizes, and then increases. We have pressure, which exponentially decreases with altitude, same with density. Now, this is very important as looking at the data, mainly for temperature, pressure, and density, we notice that for temperature, there is an uneven variation in terms of temperature with altitude. As we go up to higher altitudes, temperature is not that predictable. Again, emphasizing for pressure and density, we notice that at higher altitudes, the density of the air decreases. Similar to the air pressure. We are firm in understanding and believing that properties change with altitude. But what is altitude in the first place? Altitude is defined as the vertical distance of an object or point measured from a reference level. Again, because of this definition, we have different types of altitudes depending on where is that reference level. We have 6 main different types of altitude. We have the absolute altitude, geometric altitude, the geopotential altitude, and the performance-related altitudes, which is your pressure altitude, density altitude, and temperature altitude. Let's begin defining or understanding the 3 major types of altitude. We have your absolute, geometric, and geopotential altitude. Let's talk about height. Imagine yourself flying inside this helicopter, carrying with you an infinite measuring tape. You drop the measuring tape to the ground and you measure it to be at a certain height. You request the pilot to fly at a level flight, and you notice that your measuring tape does not hit the ground anymore, so you extend it to hit the ground. You record your data and you notice that although you maintained at least a level flight, but your measuring tape does not measure the same value anymore. In this case, you are measuring altitude in terms of the local field elevation. And as you all know, based on the contours of the surface of the earth with the mountains, the hills, the valleys, this affects our measurement using the measuring tape. So, we need to find a better reference point to which everything is almost equal. And that is your sea level. Although we have different tides, different height of the sea, measuring in terms of the mean sea level, the average value or the average height of the sea, allows us to simplify our calculations of altitude. And we call this type of altitude as the geometric altitude. It's measuring altitude relative to sea level. In this case, almost all of our measurements will be equal. And lastly, we have absolute altitude. This is a measurement of the altitude relative to the Earth's center. In this case, we will consider the radius of the Earth and adding it up to our geometric altitude. This gives us our absolute altitude. Now, the concept for absolute altitude is really relevant with space vehicles, with a rocket. As we go up higher from the center of the Earth, gravity also changes. Reviewing our understanding of Newton's gravitational law and Newton's laws of motion, we get to understand what a force is. In particular, we get to see the force of gravity expressed as Fg equals big G, mass 1, and mass 2. These are the two masses you're comparing with, and R being the distance between the two masses. So in this case, measuring U versus the Earth and the radius of the Earth. We also know that a force is defined as the acceleration of a certain mass. Equating the two, force of gravity and the force of gravity, equating them together, we get an equation giving us the value of the acceleration due to gravity of a certain object at sea level, considering only the radius of the Earth. Now, if you want to get how this acceleration due to gravity changes with altitude, with height, we have to relate the two equations all together. Knowing that GO is equal to GM2 over R2 and G equals GM2 over R plus HG squared, that's your absolute altitude. Equating where they are equal, GM2, and by equating, you get an equation describing the variation of G with altitude. This variation of gravity with altitude is important, especially on aerospace vehicles, as accounting for these variations ensures that accurate performance predictions, fuel efficiency, and precise navigation computations are conducted. But we will park this equation for now, and we will use the same equation later on as we model the atmosphere. In modeling the atmosphere, we need to do some simplifications, one of which is the assumption that the atmosphere is static. And when we assume that the atmosphere is static, we may be able to use the hydrostatic equation to identify or to visualize how pressure changes with the height or the altitude of the Earth. Now, to do this, we begin by imagining a small volume of atmosphere, of air. This small volume of air exerts a force by gravity, the force of gravity given as Fa. And this force is exerted throughout this area. And with this face of this fluid reacts to such force given as P. And since this is one static structure or volume of air, the upper surface also reacts to the forces. However, this pressure that is exerted on the upper surface also needs to take account the difference in pressure with altitude. So, knowing that this entire system is static, all forces are in equilibrium, we may be able to analyze it. All the vertical components, if you sum it up, they all equal to 0. Positive downward force. So, we have P plus dP, which is your pressure exerted on the upper surface, plus the pressure, which is A, exerted, or the force of A, exerted on this surface brought about by the weight, is given as A. This is equal to the pressure, the counteracting pressure exerted to this face as well, to the entire object, giving you dP equals a negative A. Substituting A as the density of the column of air times the change in height times the gravity, giving you the change in pressure is equal to a negative sign multiplied by the density of the column of the air times gravity times the change in height. This is a differential equation explaining the variation of pressure with altitude. And this allows us to model the atmosphere in terms of changes with pressure with altitude. Now, there's one problem here. We actually have three unknowns in this equation, three variables in this equation, one of which is gravity. Gravity here is a trap card. Simply because in the earlier discussion, we understood that gravity also changes with altitude. Hence, this complicates the entire understanding of changes to pressure with altitude through the hydrostatic equation. Now, with this, we need to simplify it. We need to simplify our modeling even further, as gravity varies with altitude too. For simplification purposes, for modeling purposes, this G right here, the value that we can use for it can be the gravity at sea level. As a difference, by aeronautical convention and by agreement and by data itself, the value of gravity, the acceleration due to gravity at altitudes less than 15 kilometers is negligible. So, with that, we will use the gravity, the acceleration due to gravity at sea level for our hydrostatic equation. And again, through the hydrostatic equation, we may be able to identify the changes to pressure and its corresponding height, or we may be able to determine what is the change in pressure at a certain height, given these two constants, the pressure, the density of the air, and the gravity of at sea level. And again, since this is just a simplification, we define a new type of altitude, and that is your geopotential altitude. Your geopotential altitude is defined as a fictitious altitude. It is for ease of calculation and for ease of modeling of the standard atmosphere. The geopotential altitude is related to your geometric altitude, which is just hg, by these, or by the hydrostatic equation, knowing that delta P is equal to negative density gravity times delta hg, and that delta P is just equal to negative density gravity at sea level times delta H. We can relate the two equations all together by equating the two equations all together in terms of dP. We get dH equals G dHg over GO, and recalling from the earlier derivation that the variation of gravity is given by the gravity at sea level times the radius of the Earth squared divided by the absolute altitude squared. Substituting that into G, we get, substituting that here, we get dH equals G O R squared dHg over GO, or multiplied by the absolute altitude, giving you dH equals R squared dHg over R plus Hg. And to make the equation whole, by integrating the equation from zero height to a certain height, And by integration, we get r squared over multiplied by -1 over r plus hg with limits from 0 to a certain geopotential altitude. Simplifying and then further simplifying, we get the final equation, which explains the relationship between geopotential altitude and the geometric altitude. There is a relationship between the actual altitude that we are measuring in terms of sea level versus the fictitious altitude, which is geopotential altitude. And in summary, we explained what the atmosphere is all about, and we explained three major types of altitude. We have the absolute altitude, the geometric altitude, and the geopotential altitude. The absolute altitude is considering the radius of the Earth plus the measured height from the mean sea level, which is your geometric altitude. And then we also made a variation to the measurement of the geometric altitude by simplifying some other variables such as gravity and density. And we assume that the atmosphere is static. We get to have the geopotential altitude, which is again a simplified model of altitude relative to changes in pressure, assuming gravity does not change. And all three types of altitude is identified or included in this one equation, which is h, the geopotential altitude, is equal to r plus the absolute altitude multiplied by the geometric altitude. And that's part one of our discussion. In the second part of our discussion, we will be talking about three other types of altitude: your temperature, density, and pressure altitude. And then we'll finalize our modeling of the atmosphere by looking into the International Standard Atmosphere table and its diagram. Okay, so that's part one of our discussion on the standard atmosphere. For the meantime, please like, share, and subscribe to keep this channel growing. Thank you.